Heard Robert sing though either.
Just
Although
play the pipes.
there is a rumor that after a Guinness or two that he doesn't sound too bad, at least thought to himself.
Is that him having the Guinness or me having the Guinness?
Yes. Heard Robert sing though either. Although there is a rumor that after a Guinness or two that he. Hold on a second, I gotta mute this. Yeah, okay. Yeah, otherwise we were going to get the feedback there the whole time. All right, folks. Well, we are live now. Jim Oberkirker, I have the pleasure of being here with a very esteemed panel. We have Mark Willerth with H&P, Lord Angus Jameson. He always hates when I call him that, of course, is why I do it, right? And all the way from sunny Inverness, Scotland. And Dr. Dew is in the house. He's muted, so we can see him laughing, but we can't hear him laughing, which is probably just as well. So we've got, this is a good session. This is a follow-up session. We had some logistical issues with our annual technical forum, and this session couldn't air. But we are going to pick this up, and this really is an important topic, and I think it's starting to get more and more focus in the industry, and of course that's with WellBore Quality. There's so many different ways of measuring it. There's so many different ways of trying to understand it, and we're going to dive into several of those here today. So without further ado, we are going to start off with Mark Willerth. Mark, do you want to share your screen? Do you have something you want to share with that?
Yeah, sure. We'll see if I can pull this off in a Zoom.
This is a live fire exercise too.
Oh man. Is that working?
Yes. You are up. Yes.
Awesome. Thanks so much for having me, Jim and Ed. For those of you who don't know me, my name is Mark Willerth. I'm a Survey Technologies advisor at Helmerich & Payne. And today I was going to talk to you about what we don't know that may be killing our well bores. In the theme of general WellBore quality. Like Jim was saying, WellBore quality seems to come in many forms. It can encompass many things. You know, folks will talk about WellBore placement, tortuosity, optimizing artificial lift. Personally, I like to distill WellBore quality to a simple concept, particularly when talking to the drilling community, which is basically anything we do that adds long-term value to the well, but has a short-term detriment to drilling operations. And I frame it up that way because the fact we're giving it a new name means it's something we don't already do. The other way I kind of use, the other thing I use as an analogy is it's like a drilling diet. If I say I'm going on a diet, that means I'm not going to eat the same stuff I was always eating before, because if I was going to keep doing what I was always doing, I wouldn't call it a diet. So basically there's this idea that whatever drilling has been doing, we need to do something else to create value for our customers. And it makes sense why this would happen, because there's a fundamental disconnect between how we incentivize drilling and directional contractors and how operators get their value. You know, we create this asset that operators will own for decades, but no directional contractor has ever had an operator come back and say, you know, 10 years ago, you drilled a really nice well for me. Here's an extra bonus. You know, the directional contractor is out getting the job next week, getting the work the next pad. And so left to their own devices, the directional contractor focuses on this very short-term outlook. How can I make today's number better? And especially in the US, as we iterate and iterate on a large number of wells, we optimize our processes for how can I get that immediate metric and how can I cut out anything extraneous? You know, the theme I want to kind of push for the audience today is that there's this thought we can go back and do a lot of retrospective studies and figure out how to find a quality wellbore. I worry that's not going to be possible, because if there was any kind of data that would tell us what our WellBore quality was, North American directional drillers would have replaced it with a tool face. We would have said, rather than that WellBore quality metric I'm not getting paid for, I want another tool face. And so I worry that we're not even collecting the data we're going to need. And I want to focus my part of the discussion on sort of trends in BHA design, because I think this is a really obvious place that directional contractors have a lot of input. The directional driller has a lot of say in what kind of BHA they're going to be using and how they use it, and what that actually means for our data. And I'm going to look really briefly at a couple studies we've done to show what might be hiding in the data, I guess is what I would say. So in particular, we can think of two trends, which are reducing bit to sensor distance, because that helps the directional driller not have to project as far. They get feedback on their actions sooner. And also the tendency to use high bend slick motors. This basically gives the directional driller the highest probability of landing the curve. The quickest way to get runoff as a directional driller is to miss your curve. And so if you have a lot of motor in the hole, you can always bail yourself out. This is a graph showing drill string interference measurements from thousands and thousands of bit runs. So this is what we actually are producing in terms of drill string interference, which, for those of you who might not be familiar, impacts your survey measurements and your ability to actually know where your well is. This distribution is the assumption our industry makes if you look at a MWD error model, so the way we actually model that positional uncertainty. It works out, the math is approximately what you would expect if we were using half of the non-magnetic spacing bit to sensor that we would anticipate in our assumptions. So basically, by reducing our spacing by half, we have about 4 times as much drill string interference and a lot more uncertainty in our wellbore placement. For our customers, they're expecting us to drill long laterals at a known spacing to optimize their asset value. The reality is this excess drill string interference creates excess uncertainty in that lateral spacing. So there could be hundreds and hundreds of feet difference in uncertainty or in spacing from what we think. And this number is huge. It's much bigger than, again, the numbers we claim if you look at industry standard error models, which would say instead of having 350 feet of uncertainty, you maybe have 150 feet of uncertainty. Or in practice, if you talk with a directional driller, what's more likely is they claim they stayed inside their drilling window, plus minus 20 feet. You have a very precise spacing on your laterals. If you're not looking for the data to understand this uncertainty, you're not going to have it. If you're looking at historical wells and you are not prepared to do this kind of study, it would be very, very difficult, if not impossible, to replicate it, because it requires getting special data from the MWD tool, the raw sensor measurements, and performing specialized analysis. And on your historical wells, if you weren't thinking forward that you were going to need it, again, you might not even have this in your archives. You might not be able to tie this back to what your well is, and you might not realize this is a reason you're getting poor performance out of certain assets. Related to that is unmodeled curvature. So here's a well path in red of what you would plot using stationary surveys. But those 90-foot surveys don't capture the curvature generated by these aggressive bottom hole assemblies. If you have a 2-degree bend in your motor, it is not producing a smooth 8-degree per 100-foot curve. You'll have these narrow sections of high curvature, and then when you rotate, you'll have sections of low curvature. But that's not anything we report to a customer. You don't have this true mapping of unwanted curvature. And the result of this is if you looked at a large number of wells and you plotted different tortuosity metrics, there's a large number of them in use in the industry. The particular one I used is actually one Angus developed, and so he'll probably talk more about that. I don't want to go too deep into the nitty-gritty on it. But basically, if you take what directional drillers say at face value, the aggressiveness of your bottom hole assembly is virtually uncorrelated with the amount of curvature in your wellbore, or unwanted curvature, which is very counterintuitive. If you run the same analysis on wellbore trajectories where you actually piece together that expected curvature, so So the idea here is this black dotted line came from BHA models of expected motor yield and rotary performance. Or the way I like to say it is, the black dotted line is if you were tapping the directional driller on the shoulder and say, what do you have at the bit? Because they know it. The directional driller projects this when they're going survey to survey. If you ask them every foot, what do you have at the bit? They would give you this number. But when we plot things like tortuosity, we ignore that stuff we know. And again, if you aren't tracking this data, if you aren't tracking this stuff proactively, it's going to be very challenging to go back and split out wells that are actually low curvature, so something that might have had a less aggressive motor and have a smooth curve, versus something that has a lot of unmodeled curvature because you had a very aggressive bottom hole assembly, but then drilled a well plan that only called for 8s. So I think as an industry, what we're going to find is that we have both a WellBore quality problem that we're unsure of how to measure because we have a data problem. You know, we have not made proactive steps to collect the data we need to really do a deep dive into what our WellBore quality issues are. And another thing, because of this group, you know, we have a lot of directional drilling professionals who rely on their experience. You know, you drill hundreds and hundreds of wells. The one thing I also want to emphasize is I don't think we can trust our intuition if that's built off of high volume US land work, because you accumulate intuition by measuring your inputs and getting immediate feedback on your outcomes. And a lot of WellBore quality issues are actions we don't measure well, and they're related to things we virtually never get feedback on. You don't know about that time when you had to slide an extra amount and put a 16 in the well to land it, you know, make a really sharp curve at the end to land it. And as a result, the ESP that the operator installs a couple years later fails 6 months early. That feedback virtually never gets to the directional driller. And by the time it would get to them, they don't think about, you know, that Thursday when it was raining and they had to put in that one really long slide. So as we come into these, I think we need to have some big discussions and some good discussions between operators and contractors about what we need to do, what data we need to collect, and how we can align incentives between the operator and the contractor. Because the root of this issue comes down to this fact that what contractors make money off of is not what operators make money off of is not aligned with what contractors are incentivized to provide. And so we need to figure out what metrics really drive value, how can we measure those metrics, and how, even if we can't optimize them right now, how can we start collecting the data to really push WellBore quality and make sure we can deliver valuable assets. I'd like to thank you all for letting me speak my piece. I would remind everyone, I think Ross and Adrian talked about this previously, but it's been a couple weeks. If you are interested in WellBore positioning, WellBore quality topics, the ISCWSA has a meeting coming up April 14th and 15th. If you're not familiar with the ISCWSA, please check out their website, iscwsa.net. And also, if you are an SPE member, please go to connect.spe.org, and you can just join the technical section there. So that way we'll get your membership counted amongst our ranks. I would like to thank everybody for your time, and I don't know if we're doing questions now or if we want to wait until the end.
We can go ahead and do the questions now if you like. I've got a zinger that I'll have if we want to get started.
Sure.
Mark, I saw there was an article, I think, in World Oil here recently that John Lindsay, the CEO of H&P, is talking about you know, a unique performance contract that H&P is embarking in. In fact, the article had indicated that maybe as much as a third of the work that H&P is doing this week is related to this. And this is not just a time versus depth, but a quality of the WellBore and by extension, then the actual production from the wells, that there's incentivizing to that. I would expect that an element of this wellbore quality feature that you're talking about today could and should go into the use of that type of contract. Can you talk about that a little bit?
Yeah, so that's a great point, Jim. I absolutely think there is a place for putting wellbore quality metrics into performance contracts. I personally would love to see a trend that way. I think what has sort of delayed that progression is some of this issue I talked about here, where because we haven't necessarily tracked the data well up to this point, it's harder and harder for the driller to make a compelling case to the operator. This thing that I'm doing that might seem like it's slowing down your operation is ultimately valuable for you, and I would like you to compensate me for that. I think though there are more and more companies realizing this long-term value approach, the way that, if you want to shift, because there's a big shift in our industry from this, just drill approach to the we need to generate free cash flow for shareholders approach. And as you start looking, huh?
A unique concept, right?
Right. Yeah. So as we've actually gotten to this idea of maybe we should make money, we can start looking at ways to kind of optimize, because really in any other industry we would consider it's like a supply chain optimization problem. Like there is a company who is delivering a product to you, this wellbore, and then you are going to have a value add from the wellbore. And so the idea of having quality enforcement in your supply chain, while new to us, seems like it should be something that shouldn't be new.
Yeah, it's a good thing the automotive industry does that, right?
Right. Yeah.
And seatbelts may or may not work when you need them, right?
Right. Exactly. And so what I think is the first big step is to make sure we have good data and good metrics to track that kind of return.
Yeah.
Because some of these metrics, and I think this has led to some of the maybe reticence in the past to work that way, is that if you're not tracking a quality metric well, then really you're just gambling. It's because you're not really controlling it if you're not tracking it. And if it's something you can't really control, then you're not necessarily delivering on it. I mean, you could imagine an Amazon delivery style contract where they got a bonus if it wasn't raining the day they dropped off your package or something, but that would be something outside of their control. And so you need to actually make sure that we can get metrics that one, the drilling contractor can control, or the directional contractor can control, and two, that directly link to value for the customer.
Yeah.
And I think once we establish those links, it'll be easier to have that conversation.
The key problem here is what's the value of different geometry characteristics. If the operators have not gone back and defined the value of one sump that's 2 feet high, they haven't defined how much production does that cost me? Under what circumstance? A 2-foot sump might be zero cost to me in a liquids well, pure liquids well. However, it kills me in a gas well, and particularly a shallow gas well. So here I have a number of variables that I have not tied together that would make a difference to what that value statement is back to making a decision at the rig site, right? And until we make that linkage between what does my production look like, not just what the rate is, but what's the EUR of these geometric quality issues, to what is that value to EUR and IP?
Yep, and I think the kind of general problem you're speaking to there, Ed, is this: we know we have variable production, but we don't know why. We have variable performance, but we don't track enough data to link what's actually causing poor performance.
One of the things that maybe y'all haven't heard is our reservoir engineers frequently just use the straight line that we planned the well on to do the reservoir modeling. They don't go back and take in at least what the directional plot shows. And they certainly don't go back and take into account what the probabilities are of that well being somewhere in that 350-foot wide cone.
Somewhere in the neighborhood.
I know we have some questions that looks like that were coming up in the chat. I can't figure out how to load it. I was going to say one thing, Ed. I included a couple extra slides just as reminders of things we've talked about in the past. And one of the slides is a callback to a different technical forum.
Yep.
It fascinates me how we talk about collision avoidance and long laterals, because if you're talking about collision avoidance, you've already lost the game on lateral spacing. You know, if your big concern is making sure the wells don't hit each other, how are you keeping them 600 feet apart?
Yeah. Yeah. Well, Mark, Chris Marland has a question. It says, you mentioned that we don't really describe tortuosity very well. That's a good segue into Angus's talk. Many MWD and RSS systems have real-time ink and AS. Why hasn't more work been done to use those to define well path and tortuosity? That reminds me back to the famous line Jack Nicholson had, you know, the truth, you can't handle the truth. I think there's certainly an element of truth to that as well. But Mark, what are your thoughts on that?
Yeah, no, I mean, if the question is why hasn't more work been done, I think the answer is pretty simple. Operators haven't paid for it. Like I said, we optimize our process, and continuous inclination has been used primarily in a way that benefits the contractor in this case. It helps them drill the well to produce the surveys they want better, because that's what they're incentivized to do. And I do think this is more of a US phenomenon. If you look at some of the extended reach international projects where there's, I would say like a much deeper drilling engineering aspect to it. Like, if you're drilling like in Sakhalin Island and things like that, or I'm sure a number of the extended reach projects in the UK that Angus could speak to, where you really have those torque and drag concerns, where you're worried about the drillability of the well, it becomes more important to do that kind of analysis. And there have been some studies. A lot of what we've done in the US, whether we like to admit it or not, is still in the stage where if we get a bigger hammer, we get to TD. You know, if we put a little more torque into it, if we push a little harder, we can often get there. And so that gives us a little cushion in terms of not necessarily doing the precise engineering of the project that would require some of that modeling with continuous data and things like that.
Sonny Old has a question. Is there a feeling on how organized operators are on evaluating the cost of a quality wellbore? And I guess by extension, you could say the value of a quality wellbore, right? You know, there's the two sides of the coin, not to put words in Sonny's mouth. Is it improving? Are they consolidating their own operational decisions between drilling and production? I think the real question on that, does drilling and production actually even talk?
Yeah. I think that's going to be highly variable operator to operator. And from my experience, what I think you will see more of is the operator who's aware of the issues will target sort of, the last dog that bit them. So if they've had, they might have a project to figure out why pumps are failing, or they might have a project to figure out why they have problems in a field, where they do a deep study. I think it was Oxy spoke to IADD a few years ago about issues of helically buckled casing and how that was impacting production. And so you will find these isolated applications of, we have this very specific problem, we found a very specific solution to it. It's been hard to find this sort of generalized solution of, here's a good wellbore anyone can use. And that's going to take a larger effort as an industry as a whole and a lot of conversations.
This is an issue that basically individual engineers within the operators will get bit, like you say, the last dog that bit them, and they'll go and bore into it for that one specific field, for that one specific formation, and they'll hammer it down and they'll come up with a solution for that. But that individual can't push that wide enough even within the organization. And his data may not really impact other fields that much. So maybe it doesn't warrant being spread through the whole company as the solution. So even within the operator, the individuals have to be able to network a more complete answer. And then, like you say, Mark, it's like on the API survey quality thing that we were working on, being able to communicate between operators on committees like that, where we actually share what we're learning, that makes a huge difference in all of us moving forward, instead of looking at the world as, the three blind men looking at the elephant, right?
Right.
Everything's a tail, everything's a trunk, everything's the side of the elephant. That's where we are right now, and we've got to be able to put our ideas together.
And there are some encouraging signs of that occurring. Of course, our industry moves very slowly, but I know even a company like ExxonMobil, which historically has been very close with its information, is now indicating more of a willingness to share. And of course, there's other operators that have been similar to that. But I think people are seeing that this is a problem that is a little challenging to resolve by themselves. And there does appear to be a little bit more potential for collaboration with this. Mark, we have another question from Anonymous.
Okay, I was going to say just one quick thing to Ed's point. Sorry, it's just when you talk about the one drilling engineer in isolation solving their problem and it being difficult applying elsewhere, I think part of that comes back to this data problem. For in this case, saying there's unmodeled curvature from your bottom hole assembly, and the extent to which it is unmodeled, again, is a function of how aggressive your BHA is. In this case, though, if you were in one field and you always drilled with a similar BHA, these unmodeled effects that you might not capture in your data would wash out. They would still be something that, like, if you were always right here at this point in 20, I don't know if you guys see my cursor, but if you always had a motor yield expected of 20 degrees per 100, those unmodeled effects would all be similar, and you might be able to draw a meaningful conclusion just for your field. But then when you go somewhere else with a different drilling practice, you lose that learning because you don't capture the same thing.
Yeah.
Sorry, good.
That's certainly is a challenge with that. Well, do you guys have any other questions or comments?
You said there's one more in the chat. Sorry.
That was the one that I just indicated. Oh, wait, that's right. You got off onto the other thing. Let me pull that back up. Sorry. WellBore quality issues only. This is more of a comment anyway. WellBore quality issues only affects production when trajectory control deficiencies lead to drill through zones harder to stimulate, i.e. screen out risk, higher blowdown or blowdown pressures, etc. Or if geometry changes are leading to workover inefficiencies, casing deformation, coil tubing, or wireline operational problems, etc. Yeah, I don't know if I would completely agree with that. What do you think, Mark?
So I think a lot of it depends on semantics, what you want to define as WellBore quality. And that's where I tried to frame this up, for this group, talking to directional drillers. In my mind, WellBore quality, like I said, is directional drilling doing something to benefit the other groups? So it might be workovers, it might be production, it might be whatever, but it's It's something outside of the traditional directional drilling or drilling incentive structure. You know, the long-term value because of a short-term detriment. If I drill a little bit slower right now, I'm going to get that money back on the back end. And again, and mainly because that's what we aren't tuned to drive for naturally. If it caused us to drill the well faster, if you saw it in a drilling metric, then I think we would get there eventually to optimizing it. There might be kicking and screaming at times. So that's where whether you want to talk about difficulty stimulating or more expensive workovers or things like that, which of those are WellBore quality, which of those are, you know, geology, geosteering related. In my mind, it's almost a name game at that point. But the fact of the matter is there's something drilling does today that has an impact on what a group is going to do tomorrow. And we want to try to holistically optimize that value.
Well, I think that a point that could be made in this area is that if there was more collaboration and exchange of information amongst the disciplines, then I think it would be easier to make decisions, you know, based on what actually creates the most value. I think the challenge for many companies, many operators, is that they are so large, that they are so siloed, and the fact that there really isn't a firm understanding of the impacts that the WellBore quality has on the overall supply chain, then you know, it makes it almost impossible to make a decision based on the overall impact that it has on the operator, because you know these are operational decisions, and they are historically done through the drilling department, and the metric that the drilling department has may not align with that which completion or production has, and nobody ever talks to the geologist anyway, right? You know, so what? No sense in even bringing them up. They're just a nuisance that cause you to skirt around.
And I think there's an issue there with the silos in organizations that, you know, every organization has their own hammer, and so they look at every problem as their own nail. And so production might not realize their problem has a drilling cause or could be changed by drilling. Again, a simple example that's a little tangential to this, but I always find it amusing. There was a paper I read one time describing microseismic fractures along a wellbore. And basically the center of fractures drifts off of the wellbore the deeper they get. And there was this very interesting, detailed geomechanical model for why the fractures might stimulate further and further off of the wellbore the deeper you get in the lateral. And I'm not a geophysicist. I don't know about that. But I do know that if you assumed there was like a 1/4 of a degree azimuth error in the surveys, that the fractures would line up with the wellbore. And so the idea that maybe it's just some survey uncertainty, you know, because well within the ellipse of uncertainty is where all the fractures were initiating from. So sometimes there's a very simple explanation that could explain something they're treating as a much more complicated problem.
I remember one time I was teaching a class on directional drilling to an operator out in the Permian Basin, and there was a production engineer in the class. And as we were working through a problem, in fact, we were doing a problem on Angus's simulator, and I went over to chat and see how he was doing, and we were talking a little bit, and then I happened to mention something about ellipse of uncertainty. And he looked at me, he said, "What do you mean?" And I explained to him what that meant. And he said, "You mean the wellbore isn't where I think it is?" And I said, "And what's your number, Mark? I think it was 98.2%. Is that right? What's the certainty that it's not where you think it is? It's 98.2 or 98.8% or something like that." I know you're taking the time to calculate that. I don't know if you had Angus check your math or not afterwards, but
right.
But he was just completely flabbergasted. He could not believe that the well wasn't exactly where he thought it was. And I think by implication, you see where some of these decisions that come into play just don't necessarily create the most value for the well path itself.
Maybe that would, that's something we're missing in our communication, that maybe our plots that we send back to the operator, not necessarily to the legal entities, but at least to the operator, we show that ellipse of uncertainty based on the actual measurements we did. And maybe we force the operator to understand that we're taking all six, the XYZ of magnetic field and gravity field, that we're taking all six of those values and computing what that ellipse of uncertainty is all the way along the wellbore. If we plotted that ellipse on every plot that we give them back. I wonder how
long
it
would
would
take. Eyes glazed over, Ed. What does this mean?
Well, that's fine if it forces that question. That's good.
Yeah.
Because the drillers are the first place that we need to start it, and then once it gets pushed into the files, and the completion engineer comes back and looks at it and goes, "What? Wait a minute, where is the wellbore?" And the production guy looks at it a few years later and starts to understand he's not where he thinks he is. And the reservoir guy starts understanding he's not where he thinks he is.
Yeah.
Then we start moving forward again.
We have a couple more questions here, Mark. Ryan Quigg says the main issue with determining wellbore quality is frequency of survey data, which is limited to telemetry rates, especially when geosteering. Do you want to address that? I think that's kind of a statement as much as it is a question.
Telemetry can play an impact, but so I assume Ryan's talking about the fact that even if we are, producing continuous survey data, we're still going to be limited by how quickly we get that data, which is true. But I think any step in that direction is going to be there's going to be a step change from just doing 95-foot surveys.
Yeah.
One survey a stand, because this is just like the plot where say if you tap the directional driller on the shoulder and ask them where the bit is, they'll tell you a different path than what's going to be on the thing. If you give a directional driller 95 feet, they can do a lot. And they'll tell you you can put a lot in 95 feet, particularly if it's not a high curvature section. And so even going from a 95-foot survey to a 30-foot survey gives you a lot. Going to about a 10-foot survey gives you quite a lot. And personally, I can't say I've done rigorous studies to validate this. I think once you go much below that, it's harder to argue that MWD is really giving you more information versus noise past 10 feet, because the thing's mounted, if you have a probe mounted in a 30-foot drill collar, how much can it really tell you about 1-foot increments of your wellbore?
Yeah. There's another question here. Oscar Sanchez says low tortuosity is also a factor depending on technology type. Not all RSS have the same level of ink azimuth hold efficiency, much less conventional BHAs using mud motors. How do you see the quantification of tortuosity effects based on drive system type? Well, that'll take about an hour to answer.
I'd say to keep my answer kind of in the scope of what I was talking about, I would say the first thing we need to do is have a good way to measure that tortuosity consistently. To have that conversation meaningfully, we'd want to have good, robust data sets saying, here's 10 ways to drill a wellbore, and here's what they do. And right now, I don't think, particularly with our 95-foot survey intervals, we're getting that data, because it'll, you can't look at a survey record and tell me which RSS was drilling it versus, again, with 95 feet, you can steer any of them to anything.
Yeah. One last chat, and then we'll move on to Angus then, Mark. Are we also past the reserves versus production conflict? That's probably not a question that you
Let
can
let
take
me
a
answer-
stab
let me
at,
answer
right?
that one. Okay, guys, the thing with production and with the reserves, you have to use both. In order to calculate the value of the well, you have to use both. It's got to be how much, what the production rate is over time gives me what the total reserves are. And that computes out to the time value of money. So when we try to say what reserves or what production, it essentially is telling you that the engineer you're talking to doesn't understand economics of oil wells. They need to use both of them.
In bigger picture, if we're talking about reserves and production as a result of drilling practices, I already feel really good about it, because I think the issue is we don't have that discussion right now. The drilling production, the actual excavation of the borehole seems to be kind of divorced from conversations about how much oil we actually get out of it, or what the value of that is. And that's the problem we need to remedy. You know, it's almost the opposite of everywhere else. You know, we break it and now they buy it, and so hey, that's how it works. Where we need to get it unified to make sure that our drilling costs directly apply to their production value.
Right. Good answer. Well, thanks, guys. That's been a great session, Mark. Thanks so much for putting that together.
Thanks so much.
Angus, we'll bring in the main act. Ed is actually here. He's just going to sweep up the popcorn and things off the floor after the concert, right, Ed? Okay, Angus, you're going to have to unmute yourself now.
Sure. Do I just go ahead and share screen then, Jim?
Just share your screen. That's correct.
Okay. I think I'm showing everyone my emails here. Hold on. If you could answer them for me, that would be at least useful.
Yeah. Well, we could answer them. You may not like the answers, but we can always. Chris, we'll get to your question here in a moment. We'll go ahead and let Chris Marlin has a question here, but we'll go ahead and let Angus present, because I think what he's going to do is going to have some bearing on what you've asked as well.
Okay, I have to apologize that there's going to be a little bit of overlap with what Mark was saying, but having said that, saying the right thing twice is never a bad thing. So I am going to talk about quality in terms of placement as well as tortuosity. This is me. I'm the UK manager of H&P's technology division. Started in directional drilling in 1979, which now seems like an awful long time ago. So I'm very old. And most of my life I've been a directional drilling consultant, but I have to confess, most of that has been for the offshore rather than the onshore market. So I'm more of a mariner than I am a landlubber. Okay, just going to move these pictures out of the way for now. Okay, 12 reasons then why tortuosity is important. First of all, it increases torque and drag while drilling. It also reduces buckling resistance in the drill pipe. It increases drill string fatigue when rotating, and it increases drag when running casing, and sometimes get to the point where you can't run the casing. It's maybe less common onshore, but offshore that happens. When we look at the forces that are acting on drill string or casing, let's take drill string. We actually already know what the forces are, because we run a torque and drag analysis before we start to drill the well. And if you can imagine a small element of the drill string, if there's any curvature in the drill string, there'll be an upwards tension above that element and a downwards tension below that element. And the curvature causes these two forces to add together vectorially to create a thrust against the whole wall. And that's why tortuosity increases friction. There's also the weight, there's the support reaction on the low side, there's the friction, and there's the flotation effect of the drill pipe. But we know what these forces are. So it's possible for us to run a fairly detailed torque and drag analysis. There's two types of torque and drag analysis, which you might be familiar with. One is called a soft string model, and the other is called a stiff string model. And a soft string model is evaluating these forces as if there was no bending stress in the pipe, more like running a length of chain rather than a drill string. And the stiff string model is just a little bit more sophisticated. It does assume that there is bending stress. And so as well as the upwards tension and downwards tension creating a side force, the pipe itself wants to be straight, and so that creates additional side force. Okay, from that information, it's then possible to create a torque and drag analysis. Now, some of my software is now 30 years old, but if it ain't broke, I'm not going to fix it. But this is a little diagram just showing you on a well the size and the direction of the side forces in the as drilled well here. So every one of these little red vectors is the size and the sense, the tool face, if you like, of the side force on the well. And you can see there's some key points in the initial build of the well, or in a sharp curve down here. There's a lot of side force acting on the well. As you get further out into the lateral, it's not really changing very much. It's only changing out here because it's changed from drill pipe to heavy collars and the BHA on the low side. There are two tortuosity thresholds that we need to be aware of, because the reality is I could actually have some undulation in the well bore, but if I'm running a casing or drill pipe that's considerably smaller than the diameter of the bit that I used, it may be possible that I'll actually iron out these undulations and I can run a straight pipe into that undulated hole. Now, we do this anyway if we're using techniques like wagging or snaking from side to side to change the build rate. And when we're doing that, there's a certain maximum distance that we can slide before we use up the annular gap as an offset. So for example, in this, the numbers on the right here, if I was doing 10 degrees per 100 and I was going to run 13 3/8 casing in a 17 1/4 inch hole, then sliding 28 feet will be enough to give me an offset that would use up the annular gap. So you get a rough idea that it doesn't take long before you're starting to put stress into the casing. The two thresholds, this is a view looking down the well. You can see the offsets measured with continuous inclination and azimuth. If you straighten that out from the beginning to the end of a slide, then you can superimpose a red area and a yellow area. And if the offsets, when I straighten it out, if the offsets are encroaching on the yellow area, then I'm going to have some side force on the casing when I come to run it. If it's bad enough that it encroaches on the red area, I'm going to have additional side force on the drill pipe, and that's going to give me increased torque and drag, which is going to slow me down, especially in the latter part of the lateral in the well. Okay, I'm continuing my reasons why tortuosity is important. It impedes hole cleaning while drilling. It compromises the cement job quality. It causes variations in cross-section due to cuttings traps, and so it can affect production rate and it can reduce production quality. This is an interesting slide here where we were just running some tests in H&P to look at different tortuosity indices that might be candidates for an industry standard. So we looked at three tortuosity indices. Generally speaking, though, when one was high, they were all high, and when another was low, they were all low. So they're all doing a pretty reasonable job of giving you a like-for-like comparison. The difficulty is that at the moment in the industry, there are 13 different tortuosity indexes that can be used. So when someone says, I just drilled a 2.7, what does that actually mean? And of course, that depends on the maths that you're using. So one of my tasks this year is to try and get some agreement, particularly through the ISCWSA, on a standardized tortuosity index. But what we want to try and do is to show that the tortuosity index is actually one that correlates well with torque and drag. Because if it doesn't, it might be measuring undulations at a level that don't actually have any impact once you run the casing. What we're finding, though, is if you look at some of these areas here, we've got the Middle Bakken, we've got Three Forks, we've got Eagleford Shale, we've got Trend Area, and these are studies over hundreds of wells. And you can see that what's normal in one area is not necessarily normal in another area. So it wouldn't be fair to have a WellBore quality indicator where we said, well, if you're drilling in North Dakota, we expect you to drill with a 2.5 or we'll punish you for it. When actually it's very difficult in North Dakota to drill with a 2.5, but it's easy to do that in the Bakken, in the Eagleford, for example. So if we do come up with a tortuosity index, it's got to be appropriate to the area that we're drilling in. This is another interesting slide that came from a study done by the University of Texas. And they were just looking at what were the differences in production as a relationship to tortuosity. So if you can imagine, you've got average production at the origin there and average tortuosity. And we saw that as the tortuosity went up, the production loss got greater. So I know that's looking like a positive axis there, but it's actually saying what was the difference from the average. And as you got to higher tortuosity indices, generally speaking, you were losing more production. Now, I have to say these numbers, they might look large, but compared to the overall reserves, they're relatively small. So I would say that the jury is still out as to whether or not tortuosity on its own has a really significant impact on production. I would argue that it has some, but it wouldn't be the reason for drilling a smooth well. You wouldn't be drilling a smooth well because you thought you were going to lose oil by not drilling a smooth well. It's got much more to do with well placement quality than well geometry quality. Here's a large normalized production against tortuosity graph, and you can see that as tortuosity goes up, normalized production does drop slightly, but it's a bit of a scatter, and you can see there are two different areas there that are plotted with different symbols, and you can see what's normal in one area is not necessarily normal in another. Okay, reason 10, it compromises survey accuracy with the consequence that it makes geosteering more uncertain, and it compromises geological modeling uncertainty. Now, this is kind of going back over old ground here, but this idea that the geologists don't attend the drilling engineers conferences and vice versa, there is a lack of communication sometimes Some operators are much better than others, but there are some operators where the geology department's in a different country and they speak on the phone every now and again, but there isn't really a clear understanding of the limitations that drilling places on the accuracy of that well's position and what's achievable. And if it was driven by geologists, they would want to spend the money to get the highest possible quality on well placement so that it paid back in production. As a general rule, money you spend on surveying, you will always get back in production, manyfold. This is a slide that has been plagiarized many times, but it was mine originally, just for the record. So here is what you think you're drilling. Here is what you're actually drilling because of poor well placement. And as Mark said, you could be sharing space with 2 wells. And this is all just down to the size of the uncertainty envelopes. If you're worried about collision between 2 wells that are supposed to be evenly spaced, then you've already lost the plot. There's no way you're going to be achieving even production from wells that are looking like this. And it's worse than that. In some fields, you can be leaving production shadows and leaving as much as 10 to 15% of your production in the ground just because you didn't survey it adequately. What can we do then to improve placement quality? And I do want to cover this because for production, this is your biggest enemy, is poor quality of placement rather than poor quality of wellbore. Well, we can use infield referencing. Here's an example of a detailed infield referencing map, and it's showing us variations in the magnetic declination over one oil field. It can be really quite marked, and we can do that from the air, we can do it from the sea, we can do it from the land. In all due modesty, we're quite good at this, and it's one way of cutting your uncertainty in half for very little money. These days, we can also run multi-station analysis, which is a way of taking magnetic interference out of the drill string, and these services are available from people like Mark and several other competitors that will do a good job as well. Multi-station analysis will cut it in half again, roughly. And then sag correction. If the geologist knew that we were drilling without sag correction and stretch correction, when it's so easy to do, they would be absolutely horrified. Sag correction is looking at the natural deflection of the drill string, and stretch correction, as the name suggests, is just the stretch in the drill pipe. Here's multi-station analysis. Very simple. We took the raw sensor data and we plotted from the raw sensor data 3 magnetometers, 3 accelerometers. We were able to plot what it thought that the total field value was for this well. And it looked like it was up around about 50,500. Well, we know that the background field is only supposed to be 50,000 in this field. But by running multiple stations and trying various corrections on each of the axes of your sensors, we can end up with a set of corrections that would make the B total value flat and correct all the way through the survey. And it's the same here. We can measure the dip angle of the Earth's magnetic field, which is a vertical angle of the magnetic field. And if that's all over the place, there's probably some interference coming with you. Again, after you've applied a good set of corrections, it should be flat and it should be consistent around the expected background field value for dip. So multi-station analysis is well established these days and relatively easy to get your hands on as a service. And this again has just about a doubling effect on your accuracy. This is sag correction. We look at the BHA as if it's a big lump of solid steel, and of course it isn't. It's flexible, and because it's so long and especially at high angle, it's going to flex under its own weight. It means that depending on where the sensors are sitting, we might actually be measuring an inclination which is pointing to the high side of the hole or pointing to the low side of the hole. And sag correction, because we already run a finite element analysis on the drill string to determine what the performance is going to be, it's almost a byproduct of that. So that's another piece of software or a service that can be easily and inexpensively applied. And believe it or not, when you apply sag correction, your vertical uncertainty due to sag reduces by 60%. And perhaps potentially even more, but the error models allow us a 60% improvement in vertical uncertainty. It's not just an inclination issue, it can be an azimuth issue as well, particularly if you've got very aggressive bent housings. Then even with the bent housing sitting on a 90 right or a 90 left tool face, you can actually have a significant impact on the observed azimuth because of the deflection of the BHA. Okay, looking at our depths, it's interesting, somebody mentioned Sakhalin. I was asked to go out and work in Sakhalin Island for a little while, and my job there was not actually the directional drilling, it was working out where the platform was in the first place. 3 different contractors had gone out to do an as-built position and got 3 different answers. Shell, being Shell, wanted it exactly right to the millimeter, and so they said which one is right, and it was a great job for me. Really enjoyed it. But these references that we start with, unfortunately, not all operators are as pernickety as Shell is about getting your references right in the first place, but they're undetectable errors if you don't do that. And the drill floor height is a case in point. If we get that wrong, every well that comes off that platform or that rig is going to be wrong. And any error there will take the geological model with it. Everybody works from a field datum, usually either lowest astronomical tide or mean sea level. LAT is the favored one for mariners because they like their charts produced to lowest astronomical tide. So if you see you've got 10 feet at the lowest astronomical tide and you've got a draft on your boat of 9 feet, you know that you can safely go into that area at any time of the tide in the whole year. So they like LAT, but the geologists like mean sea level. And that means something even in the middle of Texas. It means something even in the middle of Siberia. I love saying this, mean sea level is the equipotential gravitational plane. I don't know what that means, I just like saying it. The equipotential gravitational plane basically means if you were to dig a trench from there to the ocean, it would fill up to that level. So we know what that is all around the world. And so getting a measurement from that mean sea level to give us a ground elevation or a mudline position, and then the drill floor above that is absolutely critical to us being able to report good quality surveys in 3 dimensions to our geological friends. Okay, so for most measured depths, the drill pipe is our reference. And we'll measure, it's pretty much an international standard, we'll say that measured depth is 0 at the soles of the boots of the guys drilling the well. And the same's true of true vertical depth. It's 0 at the soles of the boots of the guys drilling the well. You get some interesting effects when you move from a floating rig and you come in with a platform to drill the same wells, and somebody corrects the depth and nobody checks that they've actually got the sign convention wrong and puts the wells all shallower instead of deeper. They're going to be deeper if the drill floor is higher. You can just imagine how that kind of thing can go wrong. But how accurate is this drill pipe? Well, of course, we're putting the drill pipe into a nice warm well, and steel will stretch by 1.3 feet per thousand for every 1 degree Celsius that you warm it up, every 100 degrees Celsius that you warm it up. So if I started with, let's do it in feet, I start with 10,000 feet, I put it into a well, it's 100 degrees Celsius, and I've got 10,013 feet. an extra half single of drill pipe that I didn't even pay for. It's a bargain. But as far as the geologist is concerned, he's going to assume that the depths that we give him are accurate. Not only that, but I've got 200,000 pounds of steel in the BHA hanging off the end of this drill pipe, stretching it by another 15 feet, easily 30 feet of error. And do we correct for it? No, it's a geologist's problem. So why should we bother? But it's so easy to do. Sorry. I'm going to throw that phone out of the room so that doesn't happen again. Sorry about that. So when we're measuring with, well, in this case, we're looking at a picture of some coil tubing. The coil tubing is measured very accurately as it goes over a feeder line. If we're measuring with wireline, then the wireline is actually calibrated for temperature, for mechanical stretch, for inelastic stretch. When you bring it back to surface and the 0 point on the tape doesn't match up, you distribute that error throughout. So these wireline measurements are extremely accurate. But if we compare wireline logs with drill pipe conveyed logs, typically the drill pipe is going to appear 20, 30, even 40 feet shallower, just because we haven't stretch corrected that drill pipe that we measured it with. This is not an untypical well, but this is some software for doing stretch correction. And on this well, it was 3,800 meters. The mechanical strain was 2 meters. The temperature strain was 5 meters. Total strain on the whole drill string was about 7 meters. So call that 20 feet of error, maybe 23 feet, something like that. Very, very easy to do, but again, it's a quality that it doesn't affect how we get paid as drilling engineers, but it has a big difference to the reservoir engineers and those that are making the geological models. Now, we mentioned the frequency with which we survey. Here's an example of why this is important. Let's say I'm running a very aggressive slide ratio. So I'll say I'm running 50% slide ratio. So I'm supposed to be building at 5 degrees per 100. I have an assembly that's capable of 10 degrees per 100, but that's okay. I'm going to slide 50% of the time and rotate 50% of the time. So let's say that I started at point A and it was 30 degrees and I slide 50 feet with my 10 degrees per 100. And now by the time I get to B, I'm at 35 degrees. If I did that the other way around, let's say I slid first and then rotated, then A would still be at 30, B would still be at 35, but on TVD, you can see I'm in a different position. But if I've only got a survey at A and a survey at B, these two are identical. And in fact, by the time you've built up an entire curve, this slide ratio effect, sometimes called the Stockhausen effect after Ed Stockhausen, who first measured it, that TVD error is half of your measured depth interval multiplied by 1 minus your slide ratio. So as an example, let's say we're surveying every 90 feet. I've got a 50% slide ratio. The half of 90 is 45 times 1 minus a half is another half. So that's 22.5 feet of error just because I didn't survey often enough. So again, we might not notice it in drilling and we're geosteering in the reservoir. So that's fine. We can stay in the reservoir. But when we pass that data on to the geologists, unfortunately, the well placement quality is so poor that translates into a poor reservoir model with the wrong TVD. Okay, to come to the meaty bit, how about the WellBore quality itself? And there are several ways to measure tortuosity. In the olden days, and by the olden days, I mean only 20 years ago, what we used to do is we would plot dogleg severity against measured depth, and then we would look at how wiggly the line was. It's fine. It's easy to calculate. It's using the survey data. It's easy to understand, but it has some weaknesses as well. The most obvious one is the less you survey, the better you look. In fact, at one point back in the 1980s, a couple of the major oil companies used to have a tortuosity penalty. And they would look at the dogleg severities, and they would pay you less if the dogleg severity breached a certain value. Well, of course, if you saw that in the survey, all you had to do was lose that survey, and then that dogleg severity goes away. Similarly, if you were doing a correction with an aggressive assembly, and you were to, let's say you were drilling horizontally and the geologist says, I want you to come up 5 feet. Well, the directional driller will always come up half of that, and then he'll flip the tool face over and drill the second half. So you'll come up 2.5 feet, and then another 2.5 feet is needed for him to drop back to horizontal again. Otherwise, you come out through the top of the reservoir. So that's a very aggressive change, but you ended up on the same inclination and azimuth as you started. And when he does that with an aggressive assembly in one slide in a kind of double curve, all he needs to do is to lose the survey at the point of inflection, and his inclination and azimuth are as smooth as anything from one to the other, and then you don't pay the tortuosity penalty. So it's possible to miss key points, but the biggest weakness is there's just no simple comparison. How wiggly is this line compared to how wiggly is another line? One improvement on that is actually to differentiate the dogleg severity curve. So now, instead of looking at the actual dogleg severity, we're looking at the changes in dogleg severity. Now, this is actually very useful because if I was supposed to be building at 10 degrees per 100, and I do consistently, then surely you can't penalize me for tortuosity because I'm just doing what the well plan said. But if I was to do it where I was doing one slide at 2 degrees per 100 and the next one at 15 and the next one at 1 and so on, then that would create a rapid change in this graph. So this is differentiating the dogleg severity to look at the rate of change of curvature. Again, it measures consistency. It doesn't penalize planned curvature. It only uses pulsed surveys, though. It can still miss key points. There's still no simple comparison, but worst of all, it's impossible to explain this. What on earth does 0.0002 degrees per foot squared mean to anyone? So this is not a popular method of doing tortuosity analysis. Another thing that needs to be considered when we're doing tortuosity analysis is just looking at dogleg severity on its own is not necessarily revealing everything that we need to know. Let's take an example. A BHA design to give a constant dogleg severity may produce good consistency when 3D arcs are assessed for curvature. But what if one survey interval was a build followed by a drop? And it looks a bit like the picture on the left. Well, that's a consistent dogleg severity. It might be 8 degrees per 100 on each of these curves, but one's -8 and the next one's +8. So we're just looking at dogleg severity on its own, and that might not highlight that actually we've got severe undulations. So the recommendation, and this again came from Shell, was always assess tortuosity index for build and lateral turn separately, and then combine to a single index. And that's very wise counsel. Okay, so here's a very simple approach. If we add up the total vertical curvature imposed on the well, and then add up the total lateral curvature imposed on the well, by the way, that's not the same thing as azimuth change. When you're at very low inclination, you can make massive azimuth changes without creating curvature. you have to take the azimuth change multiplied by the sine of the inclination to get the curvature across the well bore. So if you can imagine looking down the well, a high-low side curvature comes from the build. The left-right curvature comes from what's called the effective turn, or sometimes the lateral dogleg. And that's not the same as the azimuth change. Anyway, you add them up, you calculate at the end the square root of the total vertical curvature squared and the total lateral curvature squared, divide that by a normalizing curvature for the well type, say 90 degrees. And this is more akin to total curvature over planned curvature. And it doesn't directly discriminate against using higher dogleg severity tools, but in practice, tools that have higher dogleg severity very often generate more curvature when they're correcting as well. So it tends to show them up anyway. So if we use a more aggressive assembly, then it will cost us in tortuosity, no matter how well we drill the curve. Okay, so here's the process. Calculate the build and the turn for each interval. Calculate the lateral dogleg, sometimes called effective turn. It's just the turn times the sine of the inclination. Calculate the total build, which is the sum of the absolute value of all the individual builds, the total effective turn, and then our tortuosity index can be the square root of total vertical curvature squared plus total lateral curvature squared divided by 90. I'm just suggesting 90 as some kind of normalizing value. So here's a histogram of some results. Believe it or not, this is results from 1,500 wells. And you can see that you get an average of about maybe 2.4, 2.5, something like that. And it's pretty well normally distributed. And once you get above tortuosity indices of about 4, you're out in the asymptotes and you really want to have a conversation with the directional driller about painting the line, and that he should try rotating from time to time. Okay. Now, what about continuous data, high resolution data? This has been mentioned quite a few times. There is an issue with it in that if you take high resolution data just as it stands, the measure depth difference between two observations might be very small, and the noise in the observations might be very large. And so it looks as though it's incredibly tortuous because you built apparently half a degree in 1 foot, which looks like 50 degrees per 100. So there's a better way of handling it than just using the raw high resolution data. But it's very useful to include high resolution data because it allows you to assess true motor yield functions. It models a true trajectory in 3D. It doesn't miss key points. It also gives you a better informed torque and drag and hydraulics analysis. And when you see the data, it helps to train DDs or automation systems to minimize tortuosity. And it allows proper assessment of impact at the two thresholds. Now, I will say this, that torque and drag is your enemy for the whole of the lateral if you've drilled a fast curve. One of the attractions of using a small slide ratio, like 20%, 30%, is because the slide penetration rate is typically only about 20% of the penetration rate that you get when you're rotating. So of course, if you can slide very aggressively and then rotate, then you'll drill a faster curve. But the tortuosity that you generate in the curve is then experienced by all the drill pipe all the way out of the lateral that has to overcome the friction, and it can give you steering problems, it can give you weight on bit problems, and so on. And so this continuous data has been educating people that actually it's much better to drill a slow but smooth curve, and you'll finish up landing at TD earlier than you would do if you drilled a fast curve and then went into a It's not untypical to have a 10,000 foot lateral these days. And all of that 10,000 feet is fighting torque and drag in the curve all the way down. It turns out that the killer region is in the 60 to 90 degree region. That's where torque and drag will eat your lunch. If you're tortuous between 60 and 90 degrees in the curve, then you will have a slow lateral and you may not even be able to steer in the last couple of thousand feet. So from that point of view, slow and sure in the curve, and you'll get there quicker in the end. Nobody pays their surgeon a bonus for rushing the job. Okay, so how do we normalize this high resolution data? Well, one method that was proposed by University of Texas was to use the arc to chord threshold method. In other words, you only include surveys where that survey would create a curve where the arc to chord correction exceeds a sensible limit. Now, I've done this on a lot of wells now, and I suggest that a common standard of about ½ an inch is about right. It ignores micro doglegs within the annular gap. It can be used with continuous data, because all you're doing is you're going along the data until you've got a survey in that continuous data that gives you a decent bit of change of attitude, where the arc to chord correction is more than ½ an inch. And it more accurately indicates casing or completion risks as well. So here's some continuous data. I suggest that this method be used anytime observations are less than 10 feet, because even gyros can show up high tortuosity. So here's the azimuth is not too bad, but the inclination is following that very distinct slide rotate pattern. If you're interested in the mathematics of how to do the arc to chord correction, you should probably get out more. This will be made available in the presentation if you want to go off and set up a spreadsheet to do it. Okay, so here's the outcome. As you've moved along through the continuous data, it says, well, when I got to this point here, the arc to chord correction was more than ½ an inch. So I'm going to keep that survey, and then I'll carry on until I get another decent bit of curvature. I'll keep that survey, and you'll see that it's taking several surveys in the rapid change in inclination, not so many in the rotate section, and then more in the rapid change. And this is a very easy thing to do. You can do this in an Excel spreadsheet, and that then allows us to make use of the true geometry of the well without creating unnecessary alarm from tortuosity that isn't really there. Okay, this is just to emphasize again that with one operator, ConocoPhillips, don't mind me telling you that they gave us about 2,500 wells and said, can you analyze this for tortuosity? And their averages were pretty much the same, no matter where we were. But interestingly, this region here had a much longer tail, and this was because there was a lot of geosteering. It was a very broken reservoir area. So you might expect that higher tortuosity where there's more geosteering. In this region here, the average was still the same, but the tail dropped off quite rapidly. So where you might say in this region that a tortuosity index of greater than 4 is worth looking at, here, tortuosity greater than 4 wasn't uncommon at all, but you might want to go and look and see what was happening when the tortuosity index exceeded 10. Get the idea. It's not a simple number to use as a comparison. It's got to be a number that's appropriate for that basin or for that region. We ran a study of 1,200 wells where what we did was we looked at the tortuosity index and tried to kind of normalize it against the maximum dogleg severity, which is an indication of how aggressive the assembly was. And it was quite interesting. As a rough guide, the tortuosity index averaged out around the maximum dogleg severity divided by 6. So that was quite telling. The more aggressive you make the assembly, the more tortuosity you're going to generate, even in the same well profile, almost no matter how good the directional driller is. Okay, so what we're going to do next is we're going to collate some tortuosity index calculations from around the industry. We've already done this part. We've prepared about 2,500 wells now using a generic stiff string torque and drag study. And then we've prepared tortuosity index values for these same 2,500 wells. And we're now checking which formula best correlates to torque and drag. So we've got an idea already, but I want to just throw this out there because it may be that some of the people listening are using a tortuosity index every day that's relatively easy to calculate. If you are, can you send it to me? Because we're not precious about our suggestion. All we want to do is come up with a good tortuosity index that's easy to understand, easy to implement, and truly informative, actually telling you, yes, this is a high torque and drag well, without running a full stiff string analysis every single time. Okay, so just some conclusions at the end of all that. Tortuosity increases torque and drag and the risk of tool or casing failure. It certainly doesn't help production, and in some cases it may hinder. We also conclude that 3D tortuosity indices are better than 2D. And last conclusion, a standard calculation would be very helpful to the industry. If you've got a good candidate for that, send it to me and we'll run the analysis, check the correlation coefficients. And what we'd like to do is to present to the industry the best of all the ones that have been submitted and see if we can get an agreement to all use the same one. Okay, that's the end of my presentation. For those of you that survived all the way through, I just want to congratulate you and thank both of you.
Thanks, Angus.
Sorry, I went on a little bit longer than I planned to, but if there's any questions on that, then I'll take those.
No, I'll be fine. You know, Angus, I'll make a comment here initially. I don't know, is your wife on? There's 3 of you on the panel that have logged in. I think Mark has hacked your.
Well,
there's 3 of you there.
But, all 3, so I have no idea what happened there.
Yeah, I don't either. One, I'll make a comment. We do have a couple questions coming up, or questions and comments. Is that we certainly support this effort to standardize the tortuosity index. I think that's you don't get what you expect, you get what you inspect. And if you don't have a consistent way of measuring, it's very difficult to operationally perform to a level, because, like Mark has indicated, you've talked about, you can hide surveys, you can hide slides. I think that's a very poorly kept secret within the directional drilling industry. Understanding the impacts, and then having something to grade against. I actually personally believe that most directional drillers are competitive enough that if you give them something to drill to, that they will make their best efforts to do that, even if it's, we host a competition with a trip to Vegas in the offing. If you win the Tortuosity Index well, right, that comes into play. So that would be a good. So with there's several questions here. Angus, this one is left over from when Mark was saying. Chris got it in right at the end. He's talking about the statements with the MWD surveying. Says you want better modeling for accuracy, but at the same time state that the MWD measurements in a 30-foot collar could be questionable at any higher measurement frequency. How do we get higher resolution of survey equivalent data to measure the well path to validate the model? And I know, Angus, you have several ideas on that. We'll we'll stay with the public versions, I guess, if you're comfortable with that. But what would be a way of addressing that?
Well, there's two sources of high resolution data from the MWD. There's memory based, which will tell you after the event. So you can download the memory data, and that's very high resolution and is likely to translate into a reading every 6 inches. If you have that kind of quality of data, and the geologists are given access to that, then just standard smoothing, rolling average even, will give you a lot of value from that very high resolution data. On the other hand, if you do have a data telemetry packet that is able to give you continuous inclination and continuous azimuth, then these are very useful, but you need to be aware that, first of all, you're gathering that data with weight on the bit. So there may be an offset associated with that, just because of buckling effects and exaggeration of sag and so on. Because most times when we're taking our discrete surveys, pulsed surveys, they're taken with the mud quiet and with the weight off the bit off bottom. Having said that, it's quite possible, if you're smart with it, if you know that the data is noisy and you also know that there could be an offset, you can still use it, because you've got a discrete survey taken off bottom at the beginning and at the end of that stand. And so you could, the inclination, for example, you could quite easily say, well, what I'm going to do is I'm going to fit a function, some kind of smoothing function, to the inclination data. A cubic function is good because that will allow for a point of inflection and different curvatures and so on. So you can fit a function to that. And then you can say, well, I'm going to solve for the shape of the curve, but not for the absolute value of the curve, and basically force that function to agree with your starting inclination and your final inclination. In that case, the fitting of the function smooths the data out, and the lifting or dropping of the ends of that function to fit the off-bottom surveys gets rid of the offset. So now your two enemies of continuous data disappear. And again, that can be done with a spreadsheet, so on. What you generally need to do is find somebody who's smart, but also in their 20s, and then they'll be able to sort that kind of thing out for you with their eyes shut. You come to somebody like me, or no disrespect, Ed, we'll still want to do it on a slide rule.
And that would take a little while, wouldn't it?
Yeah, but it keeps you in a job in your old age, you know.
There you go. There you go. And you're not relying on batteries. So the Bill Lesso has a comment. It's actually less than 3 paragraphs, so I guess you're in pretty good shape. UT's defined large survey tortuosity meets your tortuosity requirements. Let's discuss. I think that's a comment. And you know where to find Bill, I would assume. Huh?
Yes. Yeah. I don't know if he might have actually been thrown out of that pub, but I usually know where to find him.
Well, that could be true of any number of pubs anywhere in the world, right?
So I'm afraid you broke up a little bit in the middle of the comment, though. So what was Bill's contribution?
He said that UT's defined large survey tortuosity meets your tortuosity requirements. Let's discuss that. So he's inviting a discussion on that. I don't think he means online here, although I could, if you want to, I can give him the ability to speak, but you know how dangerous that would be, right?
I'm okay. I've got a packed breakfast. I'd love to hear Bill chip in.
Okay. Let me go ahead and bring him on. Bill, are you where you can talk? If you just put a, yep, do it at your peril. Well, that's what we were saying, more or less. So, oops, let me go. I'll tell you what, I'll bring him on. We'll get the other questions going, and then I'll bring Bill in. Okay, so we'll get these other questions out of the way, and then I think the discussion with Bill would be good after that. Is the plan to also collate information not only on tortuosity indices, but on operational issues, risks that could be tied back to generic stiff string torque and drag calculations?
Yes. One of the things that would be very helpful is if people are submitting data from their own databases, if they have any additional information that they could supply with that, even just, how long did it take to drill this well? Then we can look for correlations between the tortuosity index and the time that it took to drill that well. Now, if we have enough data, then, if you look at kind of I love saying this, the semi-interquartile range, that makes me sound stupid. But if you kind of leave out the outliers and you just look at the sort of average, then you can draw some interesting conclusions from that, I'm quite sure. One of the things that I've asked for, but only ever been given on terms that I'm not allowed to make it public, is information like how many twist-offs we had in that field, and how many tools we wrecked, and how many ESPs are still down there in 2 halves. That's actually very helpful, but it's not the sort of information that people really want me to put up on slides and present at the ISCWSA. But I'm quite sure that most people would agree that there's a pretty clear correlation between tortuosity and damage to equipment in the well.
Yeah, I think that would be the case. Anon E. Muss has also asked a question, how the lower accuracy of rotating continuous sink and azimuth data can be fixed so that these could be used for tortuosity indices calculations in torque and drag.
Yes, it's less accurate because of offset and noise. It's not less accurate because of the sensors. The sensors themselves are still the same sensors as we're using off bottom. So what we need is more data, and we need to be aware of the offsets. There is some deterioration in accuracy because of, this is getting into the weeds. When you're rotating, there's a centrifugal acceleration that's picked up by the X and Y accelerometers, as well as what you're getting from the inclination. So it is poorer quality data. But as I said earlier, it is possible to just use that data to give you, in effect, the shape of the well between your off-bottom surveys. And for the mathematicians in the room, if you were to use a cubic polynomial, so you've got y equals ax squared plus bx, ax cubed plus bx squared plus cx plus d, you can solve for a and b and leave the c and d to fit at the beginning and the end of the well. And in that way, you've taken the offset and the noise out of the calculation. If anybody wants to follow up on that afterwards, then you should get a life, really.
I think Mark was actually the one that came up with that equation, right, Mark? And Angus has just bogarted it from there. Is that right?
Nope, that's Angus.
Yeah,
Oh.
yeah, that was actually me. I am as sad as I look. Yeah.
But he paid you to say that, though, right, Mark?
Yeah.
Well, we have. There was a comment from Ryan. He says, "Thanks, Angus, for the presentation." Bill, you are on but muted and without your video.
Hey, can you hear me?
We can hear you now.
Yeah.
Yeah, I think I got a little video problem, but I don't want to crack your screen. So you don't need to see me, but
Actually, I have control of that element, Bill. We'll just leave it.
Anyway, yeah, it says restart needed for the camera. I plugged it in after you invited me on there, and thanks for inviting me on there. You know, because you know, Angus, you touched on a lot, you know, of you know, on a lot of the issues with tortuosity. And by the way, I fully agree with you that we need a tortuosity metric that is correlatable, cause and effect, if you will, with torque and drag analysis. And I don't think we have that yet. If we, and you know, I mean, I followed what the Rapid group has done, you know, and I think they're the accepted leaders in tortuosity calculations. And I'm struggling with the 3D TI as to what it brings to the party for the level of complication that it is. And thus I go back to Teresa Baumgarten's large survey tortuosity, which is, you know, as you probably know, nothing more than the integration to calculate a 3D curvature and then divided by the length of the section that we're talking about. You know, it's very close to dog leg severity. In fact, it would be dog leg severity if the survey interval was constant. All we're doing is, you know, all she was doing and all we have been doing with that for the last 20 years is eliminating that survey distance, which is, you know, one of the problems we have to deal with. You're very close to that. And, you know, I found that a lot of people can understand that, as it is close to dog leg severity. And I'm suggesting that we consider, you know, that as the standard. Or, and I mean, I'd really like to have the discussion, especially with the 3D TIs and the 4 different flavors of 3D TI that are floating around, as to what they're bringing to the party. And I'd ask you, you know, what do you think you know, in a standard, we want something that's simple. That's what we have in large survey tortuosity. In something that's more complicated, we want it to bring something more to the party. And do you think any of the work that Rapid has done or UT has done, or any others, I'm just singling them out, but that they have done that would bring something more to the party, that would give us that elusive link between attitude, trajectory, tortuosity, if you will, and drilling mechanics, AKA, you know, as demonstrated in torque and drag analysis?
Mm-hmm. Yes, I actually think there is additional value, and that's after an incomplete study, Bill. When I've been looking at actual wells, I found it really interesting seeing how much the vertical tortuosity works out at and how much the lateral tortuosity works out at. And it's quite clear that that some directional drillers don't seem to worry too much when they're out on azimuth, as long as their inclination is okay. And then others seem to not worry too much about being out on inclination, as long as their azimuth is okay. And I think it just depends on whether they've got a plan view or a profile plot hanging on the wall. But it's just interesting seeing how much the vertical tortuosity contributes independently of the overall tortuosity value. So you can take the area under a dogleg severity graph and divide that by the length of the well. And that's what Greta was doing. And it does give you a very simple like-for-like comparison. It does correlate with torque and drag, but on its own, generally speaking, if the torque and drag, if the well is longer, the torque and drag is bigger and the tortuosity index is bigger. But if you normalize it against well length, it's not as clear a correlation. We've found that a high tortuosity index. When I say we, I actually mean my colleagues in DrillScan. They found that a high tortuosity index, just in that one bit between 60 degrees and 90 degrees in the curve, is what eats your lunch in the lateral. And so that's up and down rather than left and right. So by splitting it up, I suspect, say this is an incomplete study, Bill, but I suspect that there will be value in breaking up the tortuosity index, not just into high side, low side, and left and right, but also into the various hole sections, and the correlation with torque and drag will be higher in some parts of the well than they are in others. High tortuosity in the vertical doesn't seem to do a lot to torque and drag, but it certainly does in the latter part of the curve. So I am sorry, that's a very incomplete answer, but I really think that there is value to be had. We just haven't distilled it down yet.
There's really a lot of value in breaking it up for comparing it against the production results, that each part of the whole contributes to more degradation or less degradation of the production results. And then your comment about breaking it into vertical and horizontal, plus what the total curvature is, matters with different lift systems and with different well production modes. So you may be right even in more than just torque and drag. It may be even more tied into the production results.
Well, I take your point in that what I have seen with the simple tortuosity calculation, there's no way it's going to work across the entire well. And I mean, I feel that we have to divide the well into 3 or 4 sections, if you will, the step out, the build to horizontal, and lateral. And most of the things that I've been wanting to look at is what's going on in the lateral in terms of lateral tortuosity, where inclination and azimuth changes have basically the same effect because you're at 90 degrees and all that. Yeah. And, you know, I can't prove it, but I can state it empirically that large survey tortuosity does not work in comparing across those 3 sections. So, you know, if one of the tortuosity indices do allow us to look at tortuosity, you know, and I'm really intrigued by what you found in the 60 to 90 degree range, you know, which is also one of the buckling ranges and the one of the probably the point of the highest compressional load, if you will, thus a large impact on tortuosity. But I mean, I also see a lot of problems in the below S-shaped well in the step out when we go back to vertical, where of course the buckling limit is close to 0, and we get, you know, tremendous helical buckling crossover, if you will, that most places can't quantify. So there's tortuosity issues in both the step out section and the build, and then and probably less in the lateral. It probably doesn't matter as much in terms of drilling mechanics in the lateral, but, you know, going to Ed's point that it has an impact on production is quite possible. And one of the issues that I had going back to Teresa's paper where she discussed this was that, you know, I found if you found a lease that had enough wells in it, and I was looking at some of the Pioneer leases that had 30 or 40 wells in it, where it was a lot of the same type of things, and you could take a look at tortuosity versus either initial 24-hour test production or long-term production or even EUR, that you could actually see something of a correlation, i.e. with an R of about 70%, which I thought was pretty darn good. You know, I think when you look at too many wells across too many leases, you get too many different things to see what's going on in production. But you know, that heartens me to believe that there is a link to lateral tortuosity and production, you know, on that side of things. So we kind of have two problems to address with tortuosity: is what's going on, you know, as Mark said, in what the operators are trying to do in creating additional value in the well, as opposed to what us, the well constructors, are trying to do to create our value, basically. And those things aren't aligned. And I mean, I think Ed's been pushing, trying to get that going, and we've had discussions on that. But, you know, so we have that production issue, and then as well as we have the drilling mechanics issue, and we want to use tortuosity, going back to the whole premise of this thing, as an indication of that quality. So, you know, that's where we're heading. And you know, I think if we looked at the discussion on these different tortuosity indices, you know, across the different parts of unconventional laterals, if we were just looking at those, and, you know, Angus and you and I both are putting off our offshore extended reach tortuosity stuff because that may not directly apply, but certainly the investigative methodology that we're looking at here does apply. You know, that we can get this cause and effect and start to convince people that there are things we can do in this metric for WellBore quality that actually does impact that operator's quest for increased value. A little bit of soapbox there. I'm sorry about that, but yeah, let's get back to, you know, figuring out which tortuosity index we want to use.
I think one of the challenges,
you know, this might be one of these studies, though, Bill, that we go through the whole process and find ourselves back where we started. That there was nothing wrong with just taking the area under a dogleg severity curve, and dividing it by the length of the well. And if that's the best outcome, then so be it. But that's research and development for you, you know. I just a little story which you will enjoy, but about 30 years ago, I came up with a brand new mathematical formula for calculating wellbore position, which was so much better than minimum curvature. And I probably spent 2 months on it. I got paid by Shell to do it as part of the research budget. And then I ran it on real wells, and wells moved by about typically 6 inches at the end of a 15,000 foot well. So I went to the boss and I said, I think this has been a complete waste of time. And he actually said, well, no, it hasn't. What you've done is you've proven that minimum curvature is an adequate method for determining what the wellbore is. And he paid me, so I took the money.
Yeah, good enough counts.
Yep.
Mark,
So
you have a comment?
that's the outcome of this.
well, I was gonna say, I think one of the challenges we have here is that we're expecting there to be one metric that predicts everything that could go wrong on the well, and that just seems like it's not going to happen. You know, a simple example, talking about production, for instance, or the placement of a sump. Most tortuosity metrics I've seen, if you have an otherwise straight lateral, where that sump is located, you know, inserting a sump in that lateral produces the same tortuosity at the end of your wellbore. But, you know, if you drill a perfectly straight lateral and hook it at the end, that's clearly going to give you a better result than if you hook it at the beginning and try to drill a straight lateral. So there's some feature we're not capturing. You know, some issue we're going to have tracing calculations to outcomes. And I don't think we're going to have a single silver bullet, but hopefully, because let's come back into it's not necessarily, we were saying, you know, we want a simple metric. What we really want is a predictive metric. We want something that like, we want to know when we're kicking off and landing the curve, do we need to take remedial action to still have a productive well? You know, before we've drilled a bad well, we need to know something's happening. And that's where we are.
To some extent, we do have that, Mark. We can model for any client. We can say, if you drill this with a 2.5 degree bent housing, our prediction is you will have this much torque and drag at the end, and it will take you this long to drill. And if you drill it with a 1.8, it'll take you this long. And if you drill it with a 1.5, it'll take you this long. And you know, to get from vertical to horizontal with an assembly that's capable of 20 degrees per 100, you can do it in less than 300 feet of TVD. We're so over the top in protecting ourselves against getting behind the curve. And we're creating highly tortuous curves that then create additional torque and drag just when we need it least, when we're drilling that lateral that's actually delivering the production. So I think it's possible for us to do a predictive torque and drag analysis, stiff string model, and so on, and model what is it likely to look like based on typical tortuosity generated with that type of assembly, with that type of profile. We can do that, but people want to have a sort of scoring method where they can see, yeah, we did better than we did the last time. And it's got to be a scoring method that relates to something real. And as Bill says, it's got to add value. If it doesn't add value, it's just a number.
But we also need to know how to get that score. Because if you drill the whole well and then find out if you did well, that's not going to help you as much as if you know doing X, Y, and Z will get me that high score.
No, that's right. But if the tortuosity index is being calculated live while you're drilling, and you're repeatedly doing the same bad behavior, and somebody says to you, do you know what? If instead of steering back to the line every time, you steer to parallel, you're going to cut down your tortuosity score and you're going to get there faster and everybody's going to be happy with you. There's an education associated with keeping that up to date on site as you drill.
Yeah, because it's going to be a little bit different metric than people are used to doing. You know, so I agree with you. It's going to take some thing. Well, guys, we probably need to transition now. Ed, if I think, you know, some of the stuff that you have, well, let's use as a segue for some additional segments. If you want to maybe just give an overview of, for a few minutes, of the impact that this can have on production and so forth, and with an idea of setting up some additional webinars. This is our intent, is not that this is just a one-time deal, but that we have that, because as Angus said, we have to be able to educate people as well and make them aware that these types of things exist.
I think
So, Ed, do you
also,
want to share the screen, or do you just want to talk to it about it a minute?
well, I'll share it in just a second. But I think in light of our discussion here, just the last few minutes, I want people to think about, as we're going through this, how dog legs in the vertical, dog legs in the horizontal, and how dog leg and just the total 3D dog leg impact each of the things that I kind of fly through here. So let's see, wrong button. All right, so I'm going to talk a little bit about production, a lot about production, and a little bit about facilities.
Your screen is not shared yet, Ed.
Pardon?
Your screen is not shared.
Okay, hang on a second. Share screen, there we go. How about now? There we go. You guys can see it?
Yep.
Okay. All right, so production, longest period of life of the well can last up to 100 years. There's a lot of wells in the Permian Basin that were drilled in the 1920s, and they're still online. Economics, we usually run those on 7 to 10 years, but our life is probably more like 15 to 30 on average. We go through multiple production periods, flowing, and then we have an initial artificial lift where we got high production, and we have a later artificial lift where we have lower production, and then we can potentially convert those wells to water flood or disposal. So anything that we do, any of those drilling artifacts can last for decades. And putting a dog leg in the wrong place can turn into a huge cost when I have to keep fixing that problem over and over and over again. We've all heard about the rod parts and issues with being pumping wells with a dog leg up shallow. And that's the kind of thing that I'm talking about. What's really important is that these wells are generally hyperbolic, meaning that they start off high and drop down to a low, and they have a long period of producing at a lower rate. That's when they're most sensitive to economics. So when we get into that back end, something that we leave behind can have a high impact and can cut off the back end of that curve. And it does represent a lot of production, and it does represent a lot of cash flow to the operator. And we have to remember, poor economics, no more drilling. So we're only helping ourselves by making sure that we've got it right. Most of the time with dogleg severity, our production, our high rate time period with flowing, we can get through it. We don't have any real problems. Hull drag makes functioning of tubing movement tools like setting a packer, and we have to put tension on it or compression on it, maybe a little bit more difficult, but a lot of the time we overcome those things with wireline tools or hydraulic functions. So that's not really the most important part. However, okay, this is one of those first places where we want to think about vertical dog legs versus horizontal dog legs versus total curvature. I'm sorry about that. And then that's slugging. Slugs form on the uphole side of our sumps. Fluid gets pushed uphill and it doesn't make it over the hill because there's not enough velocity. So it keeps falling, some of it keeps falling back, just like boycotting settling does in the curve. So we've got the same situation going. And eventually the sump fills up enough that it blocks the gas, pressure has to come up, and then it blows that slug out. Well, when that slug hits the next sump, because if we got one sump, you got more than one sump, you're going to have an extra large slug moving. Now we keep incorporating these things, and we have a very large slug going up the hole. Well, that's a large volume of fluid strung out over a long distance of the tubing. When it hits the choke at the surface, it's kind of like the tollway going down through a toll booth. Backs up, doesn't it? Well, as soon as that fluid stops moving, it starts falling back. So you get a bunch of fluid falling back out of these things when they hit the choke. Not a good situation because you just end up using the curve as a huge sump. And you can kill the well with that. When those slugs hit the flow lines, then you end up being choked back because the fluid flow rate design on those flow lines is for a certain volume. When those slugs hit, the volume is different and the gas fluid ratio is different. So the friction factor goes up. And so you choke back the well while that slug is moving through the line. In offshore wells, this isn't a big deal, is it? Because you're 50 feet to the production vessel. But in a lease well, I could be 1.5 miles away. How long does it take that slug to move there? 2, 3, 5 minutes? Well, if I have a slug coming up every 5 minutes and it takes 5 minutes, that well is essentially choked back the entire time. Every time it gets choked back, the gas velocity slows. Well, the pressure does go up, so it's going to create another slug at whatever sump generated everything, and it's going to keep moving. Now we hit the production vessels. All right, we end up with water going down the oil line, oil down the gas line, and gas not necessarily being measured properly, and we end up with lost production. We also end up with solids plugging. You know, if we've got sumps through there, we may scour some of them, but we can also end up with solids building up in those low points. In between the water and the solids, we eventually stop all flow from below that sump. When we have gas lift, gas runs up the high side of the wellbore, doesn't it? So long sections above 30 degrees would lead, I'm sorry, guys, long sections of 30 degrees ends up with separation. Now, generally with 2 7/8 inch tubing, you have to have 7 5/8 inch casing to accommodate those gas lift valves. So you have to have a lot bigger casing. And you may have to orient those things to the high side. Most tubing doesn't allow you to orient a series of valves. So that becomes a difficulty. If you've got that long 30 degrees where you've gas is running on the high side and you got water on the bottom side, injecting that gas, the gas needs to go into the valve to do any good. Those tight clearances between the valves and the casing then makes it hard to work it through any of the dog legs and tortuosity, increases the drag, leaves your tubing buckled and creates problems there. So gas lift is often designed so that I don't have to pull the tubing, so that I can run my next production equipment in there, so that I can run valves on wire line, all those kind of things. And then on top of that, when I have that slugging going on, it really hurts the gas lift. The gas lift is designed to work with a continuous phase situation. Maybe bubble flow, it may be mist flow, it could be just continuous liquid, but it wants a continuous steady state situation. I'm sorry again, hit the wrong buttons here. ESPs, many of you heard Shauna Clark speak a couple of years ago at the SPE, talking about ESPs. They're long devices, 100 to 200 feet long. And what that does is gives you three problems. One is shaft fatigue, one is seal and bearing failure, and the other one is staged housing wear. So one thought also is you can't run these things at too much of an angle. If you get too much of an angle, you start getting pure gas introduced into the intake of the pump. These things are just stacked centrifugal pumps. So you can imagine, many of you guys have pools. What happens when you plug up the skimmer and you're sucking air into the pump? You start getting circulation, start tearing up the pump. Excuse me. Same thing happens with the ESP, but a lot more cost. Also, the motors require a fluid blanket in order for them to disperse heat. And so they'll burn out if you have gas running up the top side. Shaft fatigue, this is one that surprised me. At 60 hertz, we're doing a 1.8 billion cycles per year. It doesn't take much dog leg before that fatigues any material you run in the hole. Those puppies a long time ago were $100,000 to repair. So I know they're a lot more than that now. You have to have a backup pump. So you're spending that money twice. You have to have a backup pump with the same kind of pump stuck in vendor stock, actually an operator stock in the vendor's yard, in order to be able to run the thing the next day. And generally what we saw was a 2-year life was required for economics to be adequate. So right there, you're talking about 3.5 billion rotations in order for this thing to pay off. Bearings and seals, you know, just like in a motor, they last a lot longer if we run them concentrically. The seals are meant to hold the dielectric oil around the motor, keep it in there and not let water into the motor and burn. So if I'm pushing the seal to the side, it tends to leak more quickly. They're multi-stage centrifugal pumps. So if I push that centrifugal stage against the side of the housing, it's going to rub a hole in the housing or wear down the stages. We end up recirculating fluid, and it doesn't end up being a very good deal. And if I'm in a competitive reservoir, the guy next to me's got a straw in the well, I lose production because he's going to be producing while I'm down, or at least it cuts my cash flow and it ruins my economics that way. So they need to stay in a straight hole. They're expensive to pull, expensive to repair, and we lose a lot of money when they're down. Rod pumps, that's in that second stage of production. They rub at every point that our drill string touches the side of the hole. We've only got between 1/8 and 1/4 of an inch wall thickness on the rod couplings, and we generally have about 1/4 of an inch, maybe 3/16 of an inch on the tubing wall. We rub it millions of strokes, and we're going to rub a hole in it. When we part that, we have to wait for a pulling unit. And if we're doing this all the time in a field developed with horizontal wells, we're constantly waiting on pulling units. So again, we lose money or lose actual money in competitive reservoirs and delay our cash flow in non-competitive reservoirs. The downhole pumps are also sensitive because those are tubes sliding within tubes, and there's a tight tolerance. You end up binding those and spending a lot more money over the life of the well on electrical costs. We actually go through those calculations when we're designing beam pump units as to how much we're going to spend and whether that's a design we want. So we also put additional stress because of that. On the bottom, it's just like pulling on your drill pipe harder. You're going to part it quicker. If we lose it, we got to go fish it. We may have to pull the tubing. Plunger lift, that's a little bit easier to get past the dogleg severity, higher dogleg severities, but we need a low delta P to push that thing up. So it's also a really low production rate tool. So we don't want friction in the well. We've got to have a good straight, smooth well bore above it to make this thing work. We talked about slugging a little while ago. There's a bunch of consequences to this that you might not think about. When that slug hits the production vessel, you can pop off the pressure relief valve and you end up with losing hydrocarbons, but you also make a bunch of environmental damage. So you're spending money to go out there and clean up the mess you just made. We send fluid down the wrong line as the fluid level rises in the vessel. We send oil to the water tank, which a lot of the time we don't find till after the water hauler's been there. And he gets to make money off our oil. We don't. We send oil down the gas line. Gas plant makes the money, but it also screws up our gas measurements until we figure it out and clean out the plate. So, you know, we end up with water sometimes going into the oil line, and that water then makes our oil a less value. So what we have to do is put slug catchers. If these slugs are large, like we generate out of horizontal wells, that vessel has to be huge, maybe the size of a railroad car, to be able to catch those slugs as they're coming through. Think about that. A vessel that large with a lot of pressure on it, that's got to have a lot of wall thickness to carry the hoop stresses. So it's a lot of money and it's difficult to place. You may not think about it, but a very little bit of fluid hitting the compressor will damage it, absolutely destroy the inside of it and destroy the engine driving it. When we have fired vessels, we end up with liquids hitting the fire tubes, puts them out, spill again. And that's about it. I'm going to leave it for production engineers and talk about more later. Hopefully we'll get a completion engineer to talk a bit. And then we'll also have a, maybe, oops, sorry. I need to stop this. Okay, somebody help me here.
You
How do I
just,
stop sharing? Okay. We'll hopefully also get a reservoir engineer in here to answer a little more about how they're modeling these and how that impacts their results. Word I got from some of the reservoir engineers I work with is they model these wells as we planned them. They don't model where we actually landed, put the well at, and they don't even bother to include where it could be. So like Angus's slide earlier, they don't take any of that into account, and close intersection and loss of volume, that doesn't show up in the models, and the models aren't then become very inaccurate, and they don't want to trust us. So that's the end of mine.
well, I think what's important with this is to demonstrate that it is a life cycle problem, that it isn't, it doesn't just affect the drilling operations, that there's a lot of other things that come into play. And I think that the more people realize that the decisions that they make in terms of well construction do have that life cycle impact, the better off we are. We've talked several times about how the directional driller certainly has a big impact on the overall economics of a well, not only from an accuracy and precision of placement within the reservoir, but then of course the quality and goes in as well. So there's a lot to that. We had a comment, Oscar Sanchez earlier had said, although tortuosity affects torque and drag as correctly stated today by the panelists, it's not the only factor affecting it. Inadequate hole cleaning also plays a role there. For a well with a low tortuosity index can also have problems, strip out the whole BHA and running in hole casing due to other variables, which is certainly true. Of course, hole cleaning is affected by tortuosity also. So it is kind of a compounding effect when you have that in place. So we, I think we have answered all of the questions. Does anybody else have anything that they would like to add?
One thing that I think is
Well, it's getting
interesting,
close to lunch. Go ahead.
looking at some of Ed's comments and the costs of some of these completion workover operations. I mean, and you compare them to the costs of drilling, they're almost on the order of like doing an open hole sidetrack. Like if you had a really bad thing, it's almost worth it to re-drill the well.
Yeah. The challenge is a lot of people don't really understand the life cycle economics. I think there are a number of companies that are certainly paying a little more attention to it. I think where sometimes the challenges are is what do you change operationally to fix it? Directional drilling, some people consider it as much of an art as it is a science, right? And it is going to be to a great degree dependent on the individual who's executing at the well site. I mean, even as we pointed out, hiding surveys or not including them can give you an incomplete picture of what's really going on. You run out of the ability to slide at the end of a 10,000-foot lateral. Well, so what was that? Well, it's just, the mud wasn't good or this or that. Well, you put a 22-degree dog leg in the curve, which was effectively hidden. It looks like 12, but it's really a 22. And as we were talking about earlier, if that occurs at the 65 degrees, it's going to have a deleterious effect on your ability to actually drill the well, and not to mention the completion, running casing, and so forth. So I think, the purpose of this one is to help to introduce the tortuosity indexes like Angus and Mark have talked about, that can become an industry standard, and then push the communications and the education to get people aware of what it is. I think many directional drillers understand what they're doing and why, and I don't think they intentionally try to drill a tortuous well. Obviously, the geology is less than homogeneous throughout, but I think more care could be placed if it was understood what the life cycle economics of their decisions were. And I think that's true for the directional drillers. I think it's really true for the company men. Sometimes the company men are the ones that are pushing some of these practices because of what they're having. Dickie Hall has made a comment that Ed has no idea what he saw. Oh, no, he didn't say that. Says the mistakes made during drilling never go away. It's like constructing a building with a poor foundation or poor plumbing. And we're very sensitive to poor plumbing here in Houston these days. So I think there's a lot of folks. I saw somebody who's actually was Canadian, whose dining room ceiling landed on their table, complaining about who in the world puts exposed copper tubing up in an attic. So I think that's a good analogy, Dickie, that introducing these tortuosities is like putting copper tubing in an exposed place of your house and then waiting for the freeze to come. So that's good. Well, gentlemen, I appreciate your participation, the audience.
Hey, Jim. Jim, you got a second?
Yeah, Bill. Seconds up. Sorry.
Yeah. No, I mean, I note what Ed and Mark just said. Who's hammer and who's nail, going back to what Mark said. And does production realize that their problem has a drilling cause? And I think Ed, you basically said no in that long list of horror stories that you listed. My God, you're making me cry. But I mean, the audience or the technical audience in production or in completion and production or fracking is kind of the hydraulic fracturing conference that's held in February, and they're not going to let us kind in there. I've been somewhat politely told that until you get your what together, we really don't want to talk to you. If you have metrics that give us an indication that we can use in our frac design, and I accept that frac isn't production, but it certainly is a step to consider. And that's something that can impact production. But until we can get together on what we say is WellBore quality, and I don't want to just harp on tortuosity, but that's the indices of quality that are tortuosity, until we get that together and then make our case, as one discipline to another, say from well construction drilling to hydraulic fracturing, and make our case and get accepted at something like the fracturing meeting. We have to convince that other discipline that we do things that screw them up, and that we can work together to solve those, because we need a production engineer or a completion engineer to instill in the company man and the well construction people that we need that extra time to do whatever we can agree on to clean up well construction, in order to get this, elusive thing that we're trying to define commercially as in quality accepted. So, the silos don't want to talk to each other. You know, I believe, as you all do believe, that you know, we probably impact what's going to be produced or the value of these unconventional wells more than anybody, though the frack people might argue that point. Fair enough. Let's have the discussion. But, you know, we've got to talk. We've got to have a technical dialogue with these different disciplines if we're ever going to change the way we do things operationally.
Bill, you kind of make the point that we need to get upper management to understand what is going on. You know, when within service companies, we split, you know, what our incentives are by what that group is doing. Sales, how many units did you get sold? Operations, how much revenue did we get because we not only did what sales sold us, but we sold on job site. Manufacturing, how many units did we actually deliver that got run? We do the same thing on the operator side. We break down what our objectives are by each silo. And as long as upper management makes those mutually exclusive, the point of that conversation is almost non-existent.
Well, somehow we're going to have to get more production, more profitability on the well spend from drilling all the way through fracking. You know, we've got to get production up, or you know, will the last person out of the room please turn out the lights? You know, the economics are going to drive it. You know, the financial people that I talk to, you know, don't want to invest in the oil field. You know, they hate it. But, and, you know, we'll get another boom in here maybe, and all will be forgiven. And then 10 years later, we'll come back and we'll be having the same argument. So we are judged by what we measure, and we measure what is easy, and it's causing problems, I believe.
Yeah, I think that's true. Well, and that's the purpose of these webinars, is to increase the awareness, to make people understand that this is a multidiscipline impact. And I think the more we do these, and the more we branch out into the other areas, I think the better off we're going to be. So does anybody have any other comments? All right, guys. Well, thanks very much for your time. This seminar will be available on YouTube shortly, probably in the next 10 minutes or so. We often have quite a number more people that view it in recorded mode versus live. So we will keep everybody apprised of anything that comes up in the future. And I think it will be good to start working on this WellBore Quality Index or Tortuosity Index. Two different things, aren't they, Bill? You know, it's almost tortuosity is one thing, but the WellBore Quality overall, I think if we can establish a holistic metric, that will go a long way towards helping to solve these problems. So thanks again, everybody, and hope to see you soon. Stay safe.
Cheers. Goodbye.